Welcome to the 9th lecture in my quantum field theory course. This time we will begin discussing the covariance of the Dirac equation. And now this is very important because one of the reasons of why we have been doing what we have been doing so far is because we wanted to find a covariant equation. The whole point is that if we go from one frame to another, the shape of physics should not change. And what did we mean by that? That means that if we had some linear operator L, for example, acting on a system, and this is 0, right? So just putting everything to one side. And then we apply a transformation such that then we have a linear transformation L prime. Our state is now represented by psi prime. We should still have the same form, right? The shape of the equations should not change, and we should be able to go from one frame to another. So that's one of the basic things that we want. And if this is satisfied, then we say that that operator is going to be covariant or Lorentz invariant. So now going to the case of the Dirac equation, which, as you might recall, is I gamma mu del mu minus m, and then acting on psi of x, right? And we said this is equal to 0. So this is what we now want to check for covariance. However, first we have to specify a few things, right? So what transformation are we going to do exactly? So if we used to have some x mu, now we want to have x prime mu. And the transformation, just like we saw, I think it was in the last lecture where we discussed the Lorentz transformations, we are going to get x prime mu by applying lambda mu nu. Keep in mind, these indices are staggered. They are not directly one on top of the other. The first one represents the rows, so this is rows. And the second one, it doesn't matter whether they are up or down or anything like that. The first one is rows, the second one represents columns. So that is by convention, okay? So just a quick reminder. And this is going to be multiplying by x nu, right? That way the nu's contract and you end up only with this mu index right there. So that is how the coordinates transform. Right? They transform as a 4 vector, right? In the end, x mu is a 4 vector, and this transformation is when we say this transforms as a 4 vector, which is terms that we are slowly going to start introducing. And if the Dirac equation is covariant, then we want it to be of this form, right? The gamma mu's will have the same representation in any sort of frame of reference because they are constant matrices. They do not depend on space or time. So of course, they will not change from one frame of reference to another. Now the space-time derivatives will of course change or can change depending on what exactly we are doing. And of course, our spinor here can also change. So this is the shape that we would like to find, okay? So we would like to start off with this, apply the transformations, and arrive at that thing right there, okay? So, well, how can we check for covariance? Now, first, let's begin by defining exactly how we are transforming our spinor, because we already know how the 4-vector transforms. Well, how does the spinor transform? So let's just say that psi prime of x prime will be some matrix S of lambda, that is of course going to be 4 by 4 because our spinor has 4 elements, so it has to be a 4 by 4 matrix. Now we don't know what this matrix is, and in fact we don't even know if it actually exists. So what we will soon do is precisely that, right? Check whether or not it exists, and if it exists, then we will see that the Dirac equation will indeed be covariant. So this is how the psi here transforms. And how can we go back, for example, from psi prime to psi? Well, in that case, we simply have to apply the inverse, right? So s to the minus 1 of lambda on psi prime x prime. So here, of course, we are assuming that s to the minus 1 lambda, s of lambda will be 1, or in this case, the identity. Okay. So that is what we want to find. So, well, how exactly can we do it? Well, let's just go into the Dirac equation and start working. So the Dirac equation, again, is I gamma mu d mu minus m acting on psi of x equal to 0. So now let's replace this spinor. So we get I gamma mu d mu minus m. And instead of this spinner here, we have s to the minus 1 of lambda psi prime x prime equal to 0. Okay, so now, well, it's not really looking particularly covariant at the moment, so let's keep working. Now this d mu we can rewrite. So we know what this d mu is by definition. It is d dx mu. And now we're going to do a little bit of a something. So keep in mind what we saw here. So here we saw this relation right here. Well, what happens if we take the derivative with respect to x nu? So on the left-hand side, we get dx prime mu, derivative with respect to x nu. This is equal to, well, lambda here is, that's simply going to be a number. It's not going to be affected by the derivative. This is mu nu. And, well, dx nu is simply going to be 1. So this is one way in which we can write lambda mu nu. And that's going to be very, very, very important. So maybe let's take it with us. So let's take it down here. Okay, so we would like to produce this in here, and that way work towards finding this covariant notation. So notice that here we have d dx mu. So if we want to have something like this, we need to introduce these primes. However, we already used the letter mu, so we will instead use nu. So we will multiply and divide by dx prime nu. Okay? And now, let's see. So let me just make sure. Okay, now we have minus m. And well, this hasn't changed. So let's just go quickly through it. Okay, and now let's rearrange our derivatives. So we get d, let's put perhaps on the left-hand side, I will put dx prime nu over dx mu. And then on the right side, I will put d dx prime nu. And then, of course, everything else. So minus m, s to the minus 1 lambda psi prime x prime equal to 0. Now, look at what we have here. So I gamma mu, and this thing right here is precisely lambda nu mu. Notice that the indices are reversed because when we first wrote it down, we had mu nu and then mu nu, but now we have nu mu. So that's why we have nu mu. Okay, so we simply swapped the indices, but it doesn't matter. It's simply notation, right? It's just the name. They are dummy variables here. Okay, and then we have d dx prime nu, which is, let me go back to the other color. So that is d prime nu. Okay, and then minus m, s to the minus 1 lambda psi prime x prime equal to 0. So now we can actually perhaps just multiply through by this s to the minus 1 matrix. So we just multiply through here, and we also have s to the minus 1. I will not write of lambda here because I don't have any space. So notice that here we have minus m times s to the minus 1. So that, of course, is not in the original Dirac equation. So let's multiply from the right by s. That way they will cancel out in the m term. So then we have I s gamma mu lambda nu mu d prime nu, and then we have s to the minus 1 minus m. It's simply a constant. That's why we can just put it to the left. S to the minus 1. Here I'm just not writing the lambda dependence. Psi prime of x prime equal to 0. So here, of course, these two, they cancel out. And now we have this mess over here. But notice that d prime nu, we can just pull it all the way to the right. We don't really expect these S matrices to be changing in space. So we are just going to take this like this and put S to the minus 1 d prime nu. And now another thing that we can do is going to be just to put this lambda all the way to the left, just to rearrange it. Again, this is a number, so that's why we can commute it with everything. And this is I, and whoops, and then lambda nu mu, and then we have s gamma mu s to the minus 1 d prime nu minus m psi prime x prime equal to 0. And now we will just do one last thing just to make sure that this looks like what we had before, because what we are looking for is I gamma mu d mu minus m psi of x equal to 0, right? So that's what the original looked like. And we would really like to get to something like this. So just maybe with a prime. So with prime, prime. So if the Dirac equation is covariant, we should be able to get to something like this. But we are not quite there. So first of all, let's here just change nu for mu. So every nu will become mu, every mu will become nu. We're simply doing a name change, nothing else. So this would be mu nu, and I'm only doing this so that it looks like what we have down there. This here would be nu, and this here would be mu. I'm just doing this so that it is very obvious what we are doing. And now if we compare these two equations, we can see that in order for them to be the same, we need that lambda mu nu s gamma nu s to the minus 1 to be equal to gamma mu. So if this is true, right? If that is true, then this means that our Dirac equation is indeed covariant. But we don't know if that is true. We do not know if matrix S exists. And in fact, let's just rewrite this equation right here. Because again, this is simply a number. So we can multiply from the right by S and from the left by S to the minus 1. So we have lambda mu nu, which is of course unaffected by the S matrix. And then S to the minus 1 S gamma nu S to the minus 1 S. This is equal to S to the minus 1 gamma mu S. So of course, these cancel out, this cancels out, and we get this nice, beautiful equation here. I'm just gonna put everything a little bit closer together. So this is lambda mu nu gamma nu. So this is basically the condition that we have to find, and it looks very interesting. Because what we have here, we are saying that the matrix S basically is transforming our gamma matrices, right? So we are basically applying the Lorentz transformation onto our gamma matrices, which can also be done with these mysterious S matrices. So if that exists, then this is all going to be nice. And well, does that exist? Well, let's keep in mind that lambda mu nu acting on our gamma nus, this is going to give us some sort of gamma prime mu, right? It's just going to give us some new representation. But we have to keep in mind what we saw in a previous video. Now, there we said that every gamma matrix representation is going to give you the same physics, right? So you can always go from one gamma representation to another, right? That's Pauli's fundamental theorem, and we proved that, and we proved in that video that it exists, that matrix, that transformation exists, and they all still satisfy the Clifford algebra, so you can just go about your life as usual. So what that means, right, because of the Pauli fundamental theorem that we proved there, what that means is that this matrix S exists. So that is good. So we know that it exists. Yay. Well, now what? So it exists. Now what? Well, now let's try to find it somehow. Right? So basically everything that we need to prove is that that this matrix also generates the Lorentz transformations. And with that, we will have found that, this is indeed, the Dirac equation is indeed covariant, right? The matrix that transforms it exists, and that matrix is also the generator for the Lorentz transformations. That's all we need. So to begin learning more about this S matrix, let's take a look at this expression here, which is very important. I will even give it a number. So we will now begin studying it a little bit. So let's take it here, lambda mu nu, and now we will work algebraically with it a little bit. So we know that gamma, let's see where I can write it. Where I can write this. So we know that gamma mu dagger is gamma 0 gamma mu, gamma 0. And we will now use this because we're going to just do some algebraic tricks so that we can basically question the S matrices. So by doing this, we have lambda mu nu here, and now let's say gamma 0, gamma mu dagger, gamma 0. Now, why do we care about this? Well, I mean, why is this legal? Well, because if we expand this, we get gamma 0, gamma 0, gamma mu, gamma 0, gamma 0. Gamma 0 squared is 1, and that we get gamma mu. Okay, if any of that is weird to you, you need to go back to my videos on mastering the gamma matrices, because at this point, you have to know that. All right, so now we can just move gamma 0 to the left, where we can commute it with this lambda mu nu here. And since the Lorentz transformation elements are all real, right? That means that lambda mu nu dagger is the same as lambda mu nu. We can just write this like this. We can just put the Hermitian adjoint up there. Okay, or rather Hermitian conjugate. Okay, so with that, what else? Well, we know what lambda mu nu gamma mu is. It is precisely that thing right there. So let's plug it in. So we have that gamma 0, and then s to the minus 1 gamma mu s, and this of course is a conjugate gamma 0. Now, since our initial expression here came from lambda mu nu gamma nu, right, and all of this is equal, that means that this is still equal to s to the minus 1 gamma mu s. Okay, so now let's just take this expression and expand this, right? Let's apply the Hermitian conjugate here, and we have a gamma 0, and now we have to reverse the order, right? So we get s dagger gamma mu dagger s to the minus 1 dagger, and then still gamma 0, and well, s to the minus 1 gamma mu s. So let's now multiply from the right with s to the minus 1, and from the left with s. That way we get s gamma 0, s dagger, gamma 0, gamma mu, gamma 0, and then we have s to the minus 1 dagger, gamma 0, and then we have s to the minus 1. Okay? S gamma 0, s dagger, gamma 0, gamma mu, gamma 0, s to the minus 1, yes. And then to the right, we have gamma mu. Now, this may look like a huge mess, but I'm going to just place some parentheses that are going to change everything. So we have s gamma 0, s dagger, gamma 0, and then we have gamma mu. And then we have gamma 0, s to the minus 1 dagger, gamma 0, s to the minus 1. But now keep in mind that if we have, I don't know, something like A, B, C, D, and we want to take the inverse of the product of those matrices, it's the same as D to the minus 1, C to the minus 1, B to the minus 1, A to the minus 1. And also, gamma 0 to the minus 1 is simply gamma 0, right? It is its own inverse. Gamma 0 squared is 1, right? So that means that we can rewrite the, well, let me begin with the things that don't change. So this first parenthesis hasn't changed. Now the second parenthesis we can write as s gamma 0, s dagger, gamma 0, and all of this to the minus 1, and all of this has to be equal to gamma mu. And now notice what we have. We have s gamma 0, s dagger gamma 0, s gamma 0, s dagger gamma 0, but to the minus 1. So we can now multiply from the right by s gamma 0, s dagger gamma 0. And when we do that, we get s gamma 0, s dagger gamma 0, gamma mu. Let's put a parenthesis there. This is equal to gamma mu, s gamma 0, s dagger gamma 0. What does this mean, right? Let's subtract this and put it to the left-hand side. So we get this minus this is equal to 0. This means that s gamma 0, s dagger gamma 0, and gamma mu commute. Okay? So this may have looked a little bit weird. And yes, this is It's just kind of a trick, right? It's something that people figured out algebraically, but this is very useful. Why? You may be like, okay, they commute, so what? Well, as you may recall from the video we made, I think it was just a few videos ago, every single matrix, right, that commutes with all, right, every 4x4 matrix that commutes with all gammas, or with all gamma mu's, is proportional to the identity matrix. Okay, that's something that we proved in another video. If you're interested, I will put the link in the description. So this means that S gamma 0, S dagger gamma 0, which commutes with all gamma mu's, is proportional, let's call the constant of proportionality B, to the identity matrix. Okay, so that is very, very important, because now we're going to be able to do a few little tricks to figure out more. Okay, and this is going to be another very important equation. Let's call it 2. 1 is already been taken. Okay, so with this, first of all, of course, note that we could write this as S dagger gamma 0, right? We are basically going to be multiplying from the left, first by S to the minus 1, and then by gamma 0. That way, S minus 1 cancels, gamma 0 cancels, so we get gamma 0 S to the minus 1 times B. Okay, so that's another interesting expression that we'll soon use, because now what we want to do is basically take the complex conjugate of this expression to see whether B is real or complex. So that's what we want to see, because this constant of proportionality is going to be very important. Okay, so just to make this sure that we are understanding what we are doing here, what we want to do now is basically find these relations between S and S dagger, because if we find B, we already know what gamma 0 is, so this expression would give us, it would tell us a lot about S and S dagger, right? So that's a lot of good information. So with that, let's see, let's take the Hermitian conjugate of this expression right there. So that would be S gamma 0, S dagger gamma 0, and we take, right, the Hermitian conjugate there, and then we get gamma 0 dagger, but gamma 0 dagger is gamma 0, so that's why. So let's write it for now, gamma 0 dagger. Then we have S dagger dagger, which is S, gamma 0 dagger, S dagger. But of course, gamma 0 dagger, it's simply gamma 0. And on the right-hand side, right, this side, we get simply B conjugate times the identity matrix. Okay, so what do we see here? We have gamma 0, S dagger. And up here, we have S gamma 0, S dagger gamma 0. So look at this. We have S gamma 0, S dagger, S gamma 0, S dagger. But we have gamma 0 to the right, gamma 0 to the left. So what we will do is multiply this equation by gamma 0 from the right and from the left. That way we get the following. We get gamma 0 times gamma 0 S dagger gamma 0. This is equal to B conjugate gamma 0 times the unity matrix. But gamma 0 squared is 1. And again, gamma 0 squared here is 1. So we end up with this S gamma 0, S dagger gamma 0, which is exactly the same as before, right? It's exactly the same that we have up there. So that means that B times the unity matrix is equal to B dagger, or B conjugate times the unity matrix. So that means that B is equal to its complex conjugate, which means B is real. Okay, so that's some very, very, very good information. Okay, so that's a good step. So we have found some information. Now we can continue. So another way in which we can get good information is, for example, by using the determinant here. So the determinant of this equation, for example, right, the determinant of S gamma 0, S dagger gamma 0 is equal to the determinant of B times the identity matrix. Okay, now the determinant of a product of matrices is simply going to be the determinant of each matrix. So the determinant of S, the determinant of gamma 0, the determinant of S dagger, the determinant of gamma 0, and this is going to be equal to the determinant of B times the identity matrix. But the identity matrix is simply, right, 1, 1, 1, 1. So we get B, 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 and a bunch of zeros. So the determinant here is simply B to the fourth. Now, what about these? Now, the determinant of S and S dagger have to be 1. Why? Because that way we get the proper Lorentz transformations that we want. Right? We talked about that in the previous lecture. So that means that this determinant is going to be 1, this determinant is going to be 1, and the determinant of the gamma matrices, you can just quickly calculate it. You can take whatever representation you want. For example, in the Dirac representation, we have it as 1, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, minus 1, 0, 0, 0, 0. So the determinant here would be 1 times 1 times minus 1 times minus 1. So the determinant of this matrix is simply 1. So that means that this is 1, so B to the fourth power has to be 1, right? So that means that B is equal to plus or minus 1. So that is, some more information. We are getting closer. Okay, so what next? So next we want to go back to some other way of gathering some information. So let's now take S dagger S, right? We want to see what's going on here. What is S dagger S? So this we can write as S dagger gamma 0 S. But we already know what S dagger gamma 0 is. That's why we wrote this actually in the first place. S dagger gamma 0 is this thing. It is gamma 0, S to the minus 1. So this is gamma 0, S to the minus 1. And we can just put the B in front, I guess. And then we have gamma 0, S. But this expression right there, we have also seen, even though in a bit of a different form. So let's go back to equation 1. It's exactly this, right? We have S to the minus 1, gamma 0, S. So that means this is this equation in the case where mu is equal to 0. So let's plug that in. So that part right there is simply B gamma 0, and then we have lambda. It used to be mu nu, but now mu is 0. So 0 nu gamma nu. Okay, what next? Well, now keep in mind that this here is an implicit sum, right? So that would be lambda 0, 0 times gamma 0 plus lambda 0 I gamma I. Okay, and why did we do this thing? Well, because now, well, first of all, let's multiply through by gamma 0. Okay, that's, I guess, the first part here. So we have B lambda, let's just multiply through by everything, I guess. B lambda 0, 0, and gamma 0 squared, that's 1, right? This is simply a number. It's just the first element in the matrix, so it's a number. So you can commute it. Gamma 0 squared is the identity, so maybe let's write it like that. I sometimes don't write the identity because everything here is a matrix, so it's kind of implied. And not everything, but almost everything. And then we have plus lambda 0 I, gamma 0, gamma I, and a B in front. Okay, so this is equal to S dagger S. So this doesn't give us that much information, but what other thing exists out there that can give us information? Well, you are right, it is the trace. So let's take the trace of this, right? There's a reason why we spent so much time in that other video just calculating trace properties. So the trace of S dagger S, this is going to be, well, first of all, notice that this, of course, is going to be greater than 0. Why? Because both of those matrices are non-negative, right? You can just go back and look at the Lorentz transformations, for example, that we've seen. They are non-negative matrices, so it's always going to be positive. Okay, so now going back to the equation, we have S dagger S, and then the trace of, you can just split it up into each element of the sum. So we have a trace of B lambda 0, 0, right, times the unity matrix, plus the trace of B lambda 0 I, gamma 0, gamma I. So now we can just take out the numbers, right? It's a scalar, you can take it out. B lambda 0, 0, trace of the identity. Now, what is the trace of the identity? It is 1 plus 1 plus 1 plus 1. it is a 4 by 4 identity, so we simply get 4 times this, so 4 times b lambda 0, 0. And then we have plus b lambda 0 I, the trace of gamma 0, gamma I. Now, what is the trace of any two gammas with different index? Well, it is 0. This is 0. If you don't know why this happens, then go back to my lectures on mastering the gamma matrices, where we proved this and many other trace properties, which we will continue to use. So if you haven't watched that, you really should, because these are things that you need to know at this point. Okay, so this is equal to the trace of S dagger S. And we know that the trace of S dagger S is greater than 0, which means that this here is greater than 0. So this means that either lambda 0, 0 is greater or equal to 1, right? We saw that this is the orthochronous lambdas, right? This is the orthochronous Lorentz transformation, which we discussed in the previous lecture. Again, if you haven't seen that, I do recommend going to check it out. And b is greater than 0, which means, of course, b equal to 1, since we already saw that it is plus or minus 1. Or lambda 0, 0 is less or equal to minus 1, right? I mean, smaller or equal to minus 1. And b is smaller than 0, which of course means that it would be equal to minus 1. So those are the two possibilities. However, as we saw, we are interested in the proper orthochronous Lorentz transformations, which of course means that this should be greater or equal to 1, right? And we can just build anything else on top of that. That's why we care about that point. So that means that b is going to be equal to 1. So we have just finally figured out what b is. So let's now go back to this relation right here. And now we can just write it like this. So b is equal to 1. So that means that, let me see, why can't I erase this? There. And perhaps I will just rewrite it to the side anyways. So what we found is that S gamma 0, S dagger gamma 0 is equal to the identity matrix. And why is this so interesting? Well, because now we can, for example, multiply from the left by first S to the minus 1 and then gamma 0. And we get that S dagger gamma 0 is equal to gamma 0 S to the minus 1. So this is very, very important properties about for the S matrix. And all of these are going to be very, very important in the future. So, it's good to have them written down somewhere. So now we understand a lot about how this S matrix behaves. Well, we know a lot of its properties, some of the most important ones, in fact. So the thing that we now need to make sure is to see that it is actually the generator of Lorentz transformations. So keep in mind that when we had x prime mu, we saw that in order for us to get there, we need to apply the Lorentz transformations to some x nu, right? That's how our 4 vectors transformed. But now let's write our Lorentz transformation in terms of just an infinitesimal Lorentz transformation. So that means delta mu nu plus epsilon mu nu. Now, if you don't know where this came from, well, I do recommend that you go back and watch my lecture on the Lorentz transformations. But just as a quick reminder, here delta mu nu is basically the identity matrix or it looks like the identity matrix, but this is just one of its elements, right? It is 1 if mu and nu are equal, it is 0 otherwise, but it's not the identity matrix because it's not a matrix, it's just going to be a number, right? And epsilon mu nu, this is what we defined to be 0 minus epsilon 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And in a similar way, we defined epsilon mu nu to be, well, something quite similar, right? And just as a reminder, we also wrote it as eta nu lambda, epsilon mu lambda, right? So we're basically rating an index. And this is well actually also how we found it like mathematically. So this is 0 epsilon minus epsilon 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So again, you can see this is anti-symmetric. So this is equal to minus epsilon nu mu. So that is just a very quick reminder of what we had found. So actually, perhaps I should put this to the side. So I'm just going to move this somewhere to the side, perhaps over there. Okay, so now what we want to do is take our S matrix and write it infinitesimally. Now, how do we write some matrix in an infinitesimal way? Well, what we do is we say, okay, this matrix is the identity, the 4x4 identity, and then plus just some infinitesimal amount times some matrix, right? Because we are dealing with matrices. So what exactly do we have here? So we're going to call that matrix M mu nu, right? It's still 4x4, so we do need those two indices. And this infinitesimal will be epsilon mu nu, right? So that of course comes from this epsilon mu nu right here. That is the whole point. And this epsilon mu nu that we have here is precisely the one that we defined here to the side. So that is that epsilon mu nu. However, there are a few considerations because we are going to want that S of lambda times S to the minus 1 of lambda to be equal to the identity matrix. So for that to be true, we're going to have to do a few changes, and we will prove this in a moment, so you'll see why. So this is minus I to the fourth. So we have to define it like this in order for this to give us 1 once we multiply by the inverse. And well, what is the inverse? Well, if we define it like this, we can define the inverse as the identity plus I over 4, and well, and then the exact same thing. So that is our inverse here. Now notice that this M mu nu is going to be antisymmetric as well because of the fact that this here is also antisymmetric. It stems from there. And now, well, let's just check that this condition is satisfied. Okay, I promised you that it is, but let's check it. So this would be S of lambda, S to the minus 1 of lambda. So this would be 1 minus I over 4. This matrix, we don't know what this is, right? This is a question mark. We want to find it. That's one of the reasons, or that's one of the things that we are doing now. So this is minus I over 4, M mu nu, epsilon mu nu. And then we multiply this by 1 plus I over 4 and M mu nu, epsilon mu nu. Okay, so let's just multiply through. So of course, the identities still give us the identity. Maybe let's stick to the same notation. And then we have these two terms will just cancel each other out, right? When you multiply this times this and this times this, they will just cancel each other out. And then we have one term that is going to be the product of these two, which will be of order epsilon squared. So to first order, we can see that these matrices do indeed act as the inverse. And considering that epsilon is infinitesimal, this is a pretty reasonable thing to have. Okay, so now we can go back to our beautiful relation that should be somewhere over here, this one. So let's go back to this relation and, well, just see what we find if we take S and S inverse to be what we just said, right? So we will just take the infinitesimal version of this equation, basically. So that's what we're doing. We're taking the infinitesimal of that equation. So I'm just going to rewrite it here. So let's take the infinitesimal version of lambda mu nu times gamma nu. And we said this is equal to S to the minus 1 gamma mu S. So infinitesimally, lambda mu nu, as we saw, well, that's simply delta mu nu plus epsilon mu nu. That doesn't look like a nu. And we multiply this by gamma nu. And then we have S to the minus 1, which we know is the identity plus I over 4 M mu nu epsilon mu nu. And then we have, well, gamma mu. And then we have S, which is 1 minus I over 4 M mu nu epsilon mu nu. Okay. So now let's just multiply through a little bit. So first, delta mu nu times gamma nu. Well, if mu and nu are not the same, then that is 0. But if they are the same, then we just get gamma mu. So we simply get gamma mu from the first product. Then we have plus epsilon mu nu gamma nu. And then we have this product right here. So first we have identity times gamma mu times identity, which is simply gamma mu. Then we have identity times, so then we have plus, this would be gamma mu times this thing. So actually there's a minus sign. So gamma mu times I over 4 m mu nu epsilon mu nu. So that is the first part, and then we multiply this, so we get plus I over 4 m mu nu epsilon mu nu and gamma mu. And then finally, in the last product, so between these two, we get something of order epsilon squared, which we don't really care about. So here, the gamma mu's cancel out, that's the same. And then we get epsilon mu nu, gamma nu, this is equal to, and now see, we have I over 4, we have a minus, so let's factor that out. So minus I over 4. We can also factor out this number here. Now keep in mind, this is a number, this is a matrix. Okay, so be very careful. This is a number. So this would be epsilon mu nu, and then we have gamma mu m mu nu minus, because we factor out a minus sign, m mu nu gamma mu. Okay, and what we have inside is simply, this is simply a commutator. So this is minus I over 4 epsilon mu nu, and then we have gamma mu comma m mu nu. Okay, and this of course has to be equal to, just to make this very clear, epsilon mu nu gamma nu. So this is the condition that we find for this mysterious M matrix. Well, what next? This kind of feels like we don't have much to do, but actually, here what we have to do is try to find which matrix satisfies this. And thankfully, some very, very, very clever people did this. And what they found is that you can write this basically taking these indices down and these indices up. We're not changing anything. We haven't changed anything by lowering these indices. It's the same matrix. And this m mu nu is the same matrix. So the products, they still correspond. We haven't done anything illegal. And now we can say, well, do you remember the gamma matrix that we called sigma mu nu? Right? The one that we defined as I over 2 and commutator between gamma mu and gamma nu. So that matrix, it seems to behave like this m mu nu, right? So if you can either try, I mean, if this is the first time taking the course, you're not really going to see this, so don't worry. We are now just going to prove that this is indeed the matrix. Now, how do you actually think of this? That requires some incredible analysis that I'm very glad we don't have to do here. But let's just take this. Let's say we had the idea of trying this out. So let's write this epsilon mu nu gamma nu. This is equal to minus I over 4 epsilon mu nu times the commutator of gamma mu sigma mu nu. Now, what is this commutator? Well, let's calculate it. So let's maybe calculate it off to the side, and then we will plug in the result. So let's calculate now the commutator of gamma mu sigma lambda rho. So this commutator is going to be gamma mu, comma, and now let's rewrite sigma lambda rho, but not in the way we did before, right? Because we know, of course, sigma lambda rho, this is I over 2 commutator of gamma mu, in this case, we are using lambda and rho, so this is gamma lambda, gamma rho, but we can also write it as minus I eta lambda rho, and then minus gamma lambda, gamma rho. So if you don't know where this came from, I also proved this in the video where we first discovered this. I think I titled it like the other gamma matrices or something. It's the first video on mastering the gamma matrices, I believe. So anyways, then we have, let's just plug it in. So we have minus I eta lambda rho minus gamma lambda gamma rho. So this commutator, we can just split now into two. So first of all, we factor out minus I, and then we have commutator of gamma mu, comma eta lambda rho, and then we have minus commutator of gamma mu, comma gamma lambda gamma rho. Okay, so the first commutator is 0 because eta lambda rho is either 0, 1, or -1. It is just a number, so a matrix always commutes with any number. Now the minus will cancel out. And now this is not very easy to calculate because it's a commutator between just a bunch of gamma matrices, but we can actually write it as an anti-commutator. So let's see the following. So what we have here is basically matrix A, comma BC, right? The commutator of ABC. So this is simply ABC minus, this would be BCA. So if we want to turn this into commutators or anti-commutators, we can do the following. We can say AB and then leave some space plus something and then times C and then minus B times CA plus something. And if we want this to be an anti-commutator, right? If we want this to be the anti-commutator of A comma B times C, we need to here include BA. But for this to not be illegal, we also need to subtract BA. So here on the side, we're going to have AC. So you can see we have BAC minus BAC. So we are not doing anything illegal. So we have minus B times the anti-commutator of A comma C. Okay, so that is a very important property that we have. That's just a general commutator and anti-commutator relation. So we have gamma mu sigma lambda rho. So now let's plug it in. So we have I times. So gamma mu, we will have here commutator of gamma mu, gamma lambda, or rather anti-commutator now, times gamma rho minus gamma lambda, anti-commutator of gamma mu, comma gamma rho. Okay, so what are these things? Well, we know that this is I times the anti-commutator of this, that's the Clifford algebra, right? 2 eta mu lambda gamma rho minus 2 eta mu rho, I just commuted it here because, again, this is simply a number, gamma lambda. So that is one way to write this. Of course, well, we can just factor the 2 to the front. That way it's just a little bit cleaner. And there we go. So that is the result from that commutator, which I will now take back to where we were. So just Control C and let's move back. So that is this anti-commutator, right? So that anti-commutator is that. Okay, so this is equal to minus I over 4 epsilon lambda rho times 2I times all of this. So here the i's that cancel out, they will give us another minus, which will turn that into plus, and then we have 1/2, and then epsilon lambda rho times these things. So epsilon lambda rho times eta mu lambda, we have lambda in both of them, so it's going to end up raising the lambda and turn it into a mu, so E mu rho, right? So that's this one just raised this index. And then we have, so there I did skip a few steps just to make this very clear. So epsilon lambda rho, this is times eta mu lambda. You can write this as eta lambda rho, and then just put the metric on the other side, so mu lambda, and that way you have your lambdas together, and that just makes it a lot more evident that you're going to have it raising the index. All right, so let's get rid of it. And then we have this multiplying gamma rho. And now we have basically the same thing. So we have minus epsilon lambda rho times eta mu rho. So this time, what we can do is we can just change, for example, the indices here so that we get, because what we would do now is this would just raise this index, but we would like it to be the exact same as here. And keeping in mind that this epsilon matrix is antisymmetric, right? Going back to what it stands for, it's right here, right? It is antisymmetric. So we can just change the order of the indices here and put a plus. So we have rho lambda, so plus rho lambda. So it's just going to raise this rho there. And then of course this goes away. And we have this gamma lambda. So notice now that what we have here, well, this is just 2 times, did I forget? No, I didn't forget an I. So what we have here, this is just 2 times the same thing. Rho is a dummy variable, lambda is a dummy variable. You can just rename any of them. So I'm just gonna call lambda rho now, it doesn't matter. So this is now rho. So you can see that these two things are the same, right? So that means that we have 2 times this thing, so it cancels out with 1/2. So we have epsilon mu rho and gamma rho. And well, I guess we used to call it nu. I guess I could have called it nu now. So epsilon mu nu, gamma nu. So that does indeed coincide. So what we just showed is that our matrix mu m mu nu is indeed sigma mu nu. And if you want to write it like this, of course, it's now sigma mu nu. So what really matters here is that the expression that we found before, right, when we were expanding our S matrix, this generator of the Lorentz transformations, we wanted to know whether or not this matrix M mu nu existed, right? And we saw that it exists. So it exists, and it is this sigma mu nu matrix. So the generator for the Lorentz transformations, right? We got to this using the Lorentz transformations, right? The infinitesimal Lorentz transformations, and with that we got to this expression. And what this means now is that this sigma mu nu, right? This 1/2 sigma mu nu operator, this is precisely going to be our generators there for the infinitesimal Lorentz transformation. So that's going to be very, very, very interesting. Now there is an additional 1/2, right? We have -1/4, not just 1/2, but that is of course because we are dealing with spin 1/2 particles. We have 2 possibilities. So in order for us to avoid double counting, there is that 1/2 factor that we included. So that also gives you some better understanding why we chose this before, right? And I believe that, yeah, we made it. So what we did, so let me just recap what we did. So we just showed that the Dirac equation is indeed covariant. That was the whole point, right? We wanted to show that these 2 expressions are equivalent, right? So that this expression is equivalent to this. But for that, we needed to make sure that this S matrix exists and that it generates the Lorentz transformations. And we just did that. We also found some other interesting properties along the way, but now we can rest assured that the S matrix is indeed the generator of the Lorentz transformations. So now there is one last thing that we want to do now that we have, well, finally proven the covariance of the Dirac equation. So now we're going to take a little bit of a look at how some things transform, because now that we know how to determine covariance, well, let's study some things, right? So for example, if we take psi of x prime, right, which we know is simply taking our psi of x and transforming it using this S matrix, then we can actually study, for example, how the psi Hermitian adjoint transforms, right? So how does psi prime, right, this Hermitian adjoint transform? Well, if we want to do that, right, we simply have to take this expression right here, take the Hermitian conjugate here, so just dagger this expression. We can just dagger it, so we get psi prime dagger of x prime. This is equal to psi dagger of s dagger. I'm going to now stop writing the of lambda. And how do we build this psi Hermitian adjoint, in case you forgot? Well, this is simply psi, well, in this case it has primes, so I will keep to that. This is psi prime dagger times gamma 0. So that's how we defined it, right? It is simply the spinor times gamma 0. Okay, so in order for us to build that, let's multiply by gamma 0 from the right. So we get psi prime Hermitian adjoint x prime gamma 0. This is equal to psi dagger s dagger gamma 0. Okay, so here on the left hand side we have psi Hermitian adjoint prime of x prime, And on the right-hand side, we have psi dagger. But what else? What we have is S dagger gamma 0. Well, what is that? It turns out that we have already seen it. S dagger gamma 0 is gamma 0 s to the minus 1 times b, but we know that b is 1. So, see, that's why it was so useful to find it. So we can write it as gamma 0 s to the minus 1. So let me try to find where we were here. So this is gamma 0 s to the minus 1. So this is simply the Hermitian adjoint here of psi before transforming times s to the minus 1 of lambda, and this of course is psi prime here. So this is very interesting because this tells us that the adjoint here transforms inversely, right? So you don't transform it from the left times s, but you rather transform it from the right times s to the minus 1, which is pretty interesting, and we will go take a look at that more in the future. All right, and now what this does is that kind of implies that a product like psi Hermitian adjoint times psi is going to transform in a very interesting way. Because if we take this and we now want to find psi Hermitian adjoint prime, psi prime of x prime, well, how is this going to transform? Well, let's see. So this would simply be just using these definitions right here. So psi Hermitian adjoint prime is psi Hermitian adjoint s to the minus 1, and psi prime transforms as s times psi. So the s minus 1s cancels out, so we get psi prime, psi Hermitian adjoint psi, which is exactly what we started out with. There. So that is very interesting. So that means that this quantity, psi prime, psi conjugate Hermitian adjoint psi, or with the primes, is what we call a Lorentz scalar, which is very interesting. All right, so that's very nice. Now, what else can we study? We can study honestly any combination, and we can, for example, now take a look at what happens with Hermitian adjoint here x, gamma mu psi x, for example. So how does this transform, right? We want to now go to the primed version. So everything but now primed. So psi prime, x prime. Well, let's do the same thing. So let's just plug in what these things are. So the Hermitian adjoint here prime, it transforms, right? We know that it comes from psi Hermitian adjoint s to the minus 1. And then we have gamma mu, and then we have s psi of x. Well, but we are not writing down the dependence. But what is this? S to the minus 1 gamma mu s. We already saw that, right? S to the minus 1 gamma mu s. It is right here. It is lambda mu nu gamma nu. So that thing is simply, so that's the same, lambda mu nu gamma nu. All right, so we can see that psi, well, with all the primes, gamma mu psi prime, this is simply going to be, well, but let's eliminate the dependence. I'm a little bit annoyed, so psi prime. So everything there is primed. And on the right-hand side, we have lambda mu nu, which we can put to the front, psi Hermitian adjoint, gamma nu, psi. So notice how this transformation occurred, right? What we do to transform it is put lambda mu nu in the front. And where else did we do that? Well, we did that, for example, with x prime mu. This is simply lambda mu nu x nu. So this product right here, it transforms as a 4 vector. All right, and that's actually very interesting because that kind of suggests that if we define a current, J mu, for example, that is of that exact form, right? So simply the Hermitian adjoint, gamma mu, psi of x, then this is going to transform as lambda mu nu, J nu of x. Which is very nice. That is going to, of course, remain a covariant, which is very nice. And that's exactly how we defined previously, right? If you go back a few videos, I think it was when we did an entire video, I think, studying the currents in the Dirac equation. And this is actually the expression that we saw back then. So it's very nice to see how that transforms. So yeah, this has been very, very, very dense. It's been a long video. But I hope that this was useful. Of course, a lot of this I understand. It may be hard to place at the moment. We are still learning a lot of like technical things. We haven't even gotten into quantum field theory yet. We're still going through all the introductions that you should understand beforehand. And we still have a long way to go with introductions. But this is all just to make sure that when we get there, we can do anything that we want. All right. So if you made it this far, congratulations. And yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.